Okay. Hi everyone. So እንደጠየቃችሁት ስለ floating point representation እና conversion explanation video ነው ይሄ. I'm going to be working off of the solution, the assignment to solution, and going hand in hand, going over the questions there and the explanations given there. Okay? So floating point representation. So floating point representation ሳናወራ በፊት አንድ በጣም or something it's based on መነጋገር ያለብን, and most of you are already pretty familiar with this, is the scientific notation. ቁጥር አጻጻፋችን ላይ ነው እንግዲህ ይሄ የሚናገረው, right? And the way the scientific notation works is you'd have one digit, right, and non-zero digit. And then you'd have your fraction point, right? And then you'd have any number of digits after, right? Times, and then you'd have a base here. Basinal, the basis of like how many symbols we're using, quantity in numbers forms እናስቀምጥ ማለት ነው. So we were talked about decimal or base 10 numbers. We've talked about binary or, base 2 numbers. We've talked about hexadecimal digits. octaloች አሉ ምናምን. So that's what I mean by base. And the base will be raised to a certain exponent. Right? So as an example, ለምሳሌ is 1.23 times 10 to the 2. ይሄ ቁጥር ማለት ምንድነው? 10 to the 2 ስል ባስ ይሄ እንግዲህ this is in base 10 form. What I'm saying is ባስር to the raised to the power of 2 ሳባዛው ዴሲማል ፖይንቱን ሁለቴ ሙቭ ማድረግ እችላለሁ ማለት ነው አይደል? 1 2 3 123 ማለት ነው ይሄ ቁጥር. If I had said 1.23 times 10 to the power of minus 2, then I would move the decimal point twice back to give 0.0123, right? If I said 0.0034 in scientific notation አስቀምጡልኝ ስል, first figure out how to move the point to the next, to just after the next non-zero digits. The next non-zero digit ማን ነው እዚህ ውስጥ? 3 ናት አይደል? So 1 2 3 ይሄንን ወዴት? ወደ ቀኝ ሙቭ ማድረግ አለብኝ. ወደ ቀኝ ሙቭ ካረኩት to reset I would have to move it back, which means negative exponent ነው የሚኖረኝ ማለት ነው. So if I move the decimal, the middle fraction point to the right, my exponent is negative. If I move it to the left, my exponent is positive. So in this case negative ነው የሚሆነው 3.4 ይሆናል. ስንቴ ነው? 3 ጊዜ ወደ ቀኝ ነው ሙቭ ያደረኩት. So 10 to the negative 3 ይሆናል ማለት ነው. So that's this number in scientific notation. If I did እቺን ቁጥር 2520 በሳይንቲፊክ ኖቴሽን ላስቀምጣት ካልኩ እዚች ጋር ኢምፕሊሲት ፍራክሽናል ፖይንት አለች አይደል? 00 እያለ so እቺን to the መጀመሪያ like just after one non-zero digit ነው የምናስቀምጠው. ያ ማነው? እቺ 2 ናት አይደለ? The first non-zero digit, the most significant non-zero digit የትኛው ነው የሚለው the most significant digit ማለት ነው. አውርተናል. the most significant bit, the most significant digit አለናል. በግራ በኩል ያለው non-zero digit ወይም bit, right? እንደዚህ ሊሆን ይችላል, እንደዚህ ሊሆን ይችላል, እንደዚህ ሊሆን ይችላል, እነዚህ. so ፖይንቱን 1 2 3 ሙቭ አደርጋለሁ. to the left move ስራኩት ኤክስፖነንት ምንድነው? ፖዚቲቭ ነው. so I do 2.52 ዜሮዎቹን ዲስካርድ ማድረግ እችላለሁ times 10 to the power of 3. This is the scientific notation. And with scientific notation we can also do it for other base numbers like binary numbers, right? So if I had እቺን ቁጥር ቁጥር ማለት ምንድነው? እዚህ ጋር እንዳለኝ 2 4 አለኝ 8 አለኝ 8 4 12 ይሄ ማለት this is 13 in decimal. ይሄንን ቁጥር in scientific notation አስቀምጡልኝ ብላችሁ again the point exists just after the least significant digit implicitly አይደለ ማይታይ ከሆነ መጨረሻ ላይ ነው ያለው ማለት ነው ይሄንን ወዴት ሙቭ ማድረግ አለብኝ to the right next to the most significant bit which is 1 2 3 እዚህ ጋር ነው እንዲሆን የምፈልገው ሲያረኩ 3 ወደ ግራ ስለሆነ ሙቭ ያረኩት ፖዚቲቭ ነው ኤክስፖነንቴ 3 ነው በዛት እስቲ አሁን ደግሞ ሌላ እንትን እንበል we'll do ይሄንን scientific notation አስቀምጡልኝ ካልኳችሁ what do I do now ደግሞ again I move it back ግን አንዴ ብቻ ነው ሙቭ ያረኩት so 10 to the 1 ይሆናል same thing back and forth right like I could do ይሄንን 1 2 3 to the next non-zero bit መውሰድ አለብኝ በስማምስ በ3 ልናልቅ ነው this is what we do times oh huge mistake actually I hope you guys caught this እዚህ ጋር በ10 ነው አባዛው አይደለም በ2 ነው አባዛው ምክንያቱም base 2 ነው it's a base 2 number that we're working with right እንዴት ዝም እንዳላችሁኝ ተስፋ አደርጋለሁ that people were confused enough they understood enough to be confused by this point it had to be 2 ይሄን ስንት ጊዜ ነው ሙቭ ያረኩት 3 ወደፊት so times 2 to the minus 3 this should tell you an important thing about binary numbers as well right what happens when you multiply by 2 when you divide by 2 binary numbers emilo and later I think you'll or just in general in your computer science education career you'll come across something called bit shifting right bit shifting ማለት ለምሳሌ 1 0 1 1 0 1 0 ቢኖረኝ እንደዚህ and I was working in like let's say እዚህ ጋር 2 ቦታ አለኝ እዚህ ጋር 3 ቦታ አለኝ shifting bits to the left ማለት ራሱን እንደዚህ እዚህ ጋር ባስቀምጥ right እቺኛው ወደዚህ ትሄዳለች እቺኛው ወደዚህ ትሄዳለች አንድ shift ያደርጋሉ እንደዚህ literally shift አረኳቸው ማለት ነው አይደል ከዛ በዚህ በኩልም እንትን አደርጋለሁ 0 አደርጋለሁ እቺ 0 ነበርች anyway በ0 ነው ፓድ ማድረጎች from the right so when I shift to the left what did I do I multiplied by 2 ማለት ነው አንድ ወደ left shift ሳደርግ በሁለት አባዛውት ማለት ነው ስለዚህ እቺ ቁጥር በሁለት ስትባዛ ይሄንን ቁጥር ይሰጠናል right shifting is the same thing except በሁለት ማካፈል so yeah bit shifting in በኋላ እንትን ትላላችሁ but anyway this is the number because with decimal point and shift ስናረግ ወይ በ10 by a power of 10 እያባዛን ወይ በpower of 10 እያካፈልን ነው with binary numbers pointun fractional pointun move ስናረግ ወይ በpower of 2 እያባዛን ነው ወይ በpower of 2 እያካፈልን ነው ምክንያቱም ይሄ like 2 to the minus 3 ማለት 1 over 2 to the 3 ማለት ነው right this is also another like arithmetic equality okay so just a few things to add here scientific notation grasp ካረጋችሁ በኋላ the components የሚለው ጥያቄ እንግዲህ እዚህ ጋር ማንቲሳ ወይም significant exponent እና sign ምንም ኔጌቲቭ ነምበር ኤግዛምፕል አልሰጣችሁም ግን ያው it's intuitive ብዬ ነው እዚህ ጋር this could just have been a negative number so sign it means whether or not it's positive or negative the mantissa is this part significant ይባላል it's this part ከለር ቀይሬ ላኩ this part this part this part oh sorry this isn't in scientific notation ይሄ part እነዚህ ማንቲሳ ይባላሉ and the exponent is obviously the exponent at the top of the base exponent not so these are the three components of a floating point representation ይሄ ማለት ምን ማለት ነው with floating point representation, the number has to be put in scientific notation. The basis of the floating point representation is scientific notation. So keep that in mind. So let's go right to so there's different floating point representations, right? Like people have come up with many mechanisms. Floating point ሲጀመር floating point የሚባለው because the point floats, right? ለምሳሌ like there's something called a fixed point representation and there is the floating point representation. Fixed point representation ማለት if I am representing a number a certain way, I'm saying I only allow 4 digits before the point and like 4 digits after the point. The point is fixed አይደለ? ከ4 ዲጂት በኋላ ነው ፖይንቱ ያለው 100% እላለሁ። With floating point, like we see here, scientific notation የሚያደርግልን ምንድን ነው? Like in reality, for the number, the point is ለምሳሌ for 123, it's after 3 digits አይደለ? እዚህ ጋር ስናስቀምጠው እዚህ ጋር ሆነ እንጂ it's after 3 digits. So I can represent the number in this way, but the point is after 3 digits. Or ለምሳሌ እዚህኛው ላይ ደግሞ it's like it has 4 digits that come after it in reality, this number. The point moves around. I'm able to show something in a standardized format, while in reality, for the actual quantity that I'm talking about, the point is in different positions. That's why it's called a floating point, right? So with floating point representation, there's many ways to do it. There's one format that we're talking about here and paying special attention to, and that is the IEEE 754 format, right? አንዱ ጥያቄያችሁ ነበር, why is it important? It's the first standard of its kind, etc. የሚለው. So with IE 754 ደግሞ there's further types. አንደኛው the one we're talking about here is called single precision, and single precision ማለት በ32 ቢት ብቻ ኮሚኒኬት የሚደረግ ነው. There's a double precision which is 64 bits, which you can guess represents a higher group of numbers with more precision, like a bigger range of numbers, right? So as we also talk about these things a lot. ለምሳሌ how many different things can I represent in 1 byte, right? Or in 4 bits. And we've talked about how like 4 bits calculating to the 4 now, 1 byte is 8 bits, so 2 to the 8, etc., right? So ለምሳሌ 4 ቢት ከሰጣችሁ በ4 ቢት ስንት ቁጥር ልትሰጡኝ ትችላላችሁ? We calculated this is question the range question, question number 8 ላይ a 4-bit signed magnitude, 4-bit 2's complementary min range cover ያደርጋል ምናምን. So the more number of bits you have, the bigger the range, right? So it's a bigger range for, where is this? If I have 64 bits as opposed to 32 bits and more precision, right? Precision ማለት ለምሳሌ let's say my number is actually like the thing that I measured is, let's say 3.456789. I could say I'm going to round it off and say 3.46, or I could say 3.4568. This is more precise than 3.4611. It is closer to the original amount, right? So with double precision you also get more precision because you get to accommodate more points, more digits, more numbers after the fraction point. Anyway, that's an aside. So we're talking about single precision, but በ32 ቢት represent የምናደርገው number ማለት ነው. Okay, so let's jump right into it, right? I'm gonna say I'm gonna use this space here to talk about, let's say this is 32 bits of space, and each one of those bits of space we will keep drawing. Okay, so the first bit, the most significant bit, is used for sign. So አሁን እዚህ ጋር እዚህ ጋር 1 አለ እስከ 32 አለ if I was being really computer sciencey ከ0 እስከ 31 ነው የምለው you would find about I mean I think you guys are going through the programming course as well so you understand what this is but bit 1 this is the sign bit and as you've been familiar in other places as well 0 ማለት it's positive 1 ማለት it's negative so just by looking at the first bit in floating point representation I can tell whether or not the number I'm talking about is positive or negative right if it's a 1 in that position it's negative if it's a 0 in that position positive no okay kaza the next 8 bits are used to determine the value of the exponent so exponents in Naradamo there's another thing we need to think about something called the bias right so let's change color and draw 8 bits and we let 3 4 5 6 7 8 these are the exponent bits so bias ምንድነው ስንል anytime we have a value of an exponent ለምሳሌ if we take let's take one of the scientific notation numbers we have here I'll write a new ones actually let's say I have 6.79 times 10 to the power of 5 and let's say I have 3.212 times 10 to the power of minus 4 right እነዚህን ቁጥሮች ልጻፋቸው ብል just እንትን ለማለት ይሄንን 1 2 3 4 5 አይደለ 79000 679,000 ነው ይሄ ቁጥሬ and then ይሄኛውን ደግሞ ወደ ኋላ ልወሰደው ካልኩ 1 2 3 3 2 1 2 yeah so this is 0.0003212 ይሄ ነው the actual value of the ቁጥር scientific notation ይሄ ነው አይደለ exponent የትኛው ነው this and this right when I say add in a bias ይሄ ካለኝ in order to put it into IEEE 754 format I take the exponent 5 for the first one and I add the bias for the 32 the single precision format is 127 right አምስትና 127 ሲደመር ስንት ነው 132 is the thing I convert into binary in 8 bits right 132ን በ8 ቢት ባይነሪ ውስጥ አስቀምጥ it will give me the value of this here same thing with minus 4 127 123 this is what I put why do we have a bias the bias allows us to cover a range that starts from the negative all the way up to positive using 80 bits as you got like I don't want to reserve 1 bit sign ለመናገር for this one ልክ እንደ larger ቁጥሩ እንዳረክ or 0 ከሆነ 1 ከሆነ ኔጌቲቭ ምንድነው ኤክስፖነንቱ ፖዚቲቭ ነው ኤክስፖነንቱ ኔጌቲቭ ነው ማለት አልፈልግም 8ቱንም ቢት ለቁጥር ቫልዩ የመጠቀም ፈልጋለሁ because it makes my arithmetic easier to not reserve like 1 bit for sign and have 7 bits actual numerical value leni like it's easier to just go ከ0 እስከ 1 ድረስ ሄጄ አንድ ድረስ ሄጄ 8 ቢት ቁጥር ስንት ፖሲቢሊቲዎች አሉ 256 አይደል ከ0 እስከ 255 is the actual numerical value the highest it life 0 ስለምትቆጠር ነው አንድ ላይ 256 የሆነው ከ0 እስከ 258 ያሉትን values I want to map them directly to a range of negative to positive so 0 ወደ ምን ማፕ ያደርጋል 0 to 1 minus 27 ይሄ ወደ ምን እንትን ማፕ ያደርጋል። ፖዚቲቭ 128 ከማይነስ 127 እስከ ፖዚቲቭ 128 ድረስ ይሄዳል right and this is because ይሄንን ቁጥር በባይነሪ ለማግኘት 127 ደምሬ ከሆነ ኮንቨርት ያደረኩት whatever I have in binary like 132 ነው ወደ ባይነሪ ቀይር ቢባል let's what we want to do 128 right which is 0 1 2 3 4 5 6 7 the 7th bit ላይ አንድ ይኖራል actually አንድ ይኖራል this is 2 to the 7 right ከ128 3 ስንት ይቀረኛል 4 ይቀረኛል 0 2 no 1 ያ 2 4 እዚህ ጋር እንዳደረጋለሁ I just converted it to binary on the fly 132 in binary is this ይሄ ከሆነ በኤክስፖነንት ቫልዩ ይሄንን ብትሰጡኝ actual exponent value እዚች ጋር ለመድረስ ምን ጀማረጋው መጀመሪያ ይሄንን ወደ ዴሲማል ቀይረዋለሁ which is 132 ከዛ 132ን ሳገኝ 127 ቀንስበታለሁ ምክንያቱም 127 ደምሬ ነው ያገኘው ይሄንን value 127 ቀንስለት 5 አገኛለሁ 5 is my original exponent value so that's why exponentoች the number of possible exponents that I can have in my single precision floating point representation range from negative 127 that's when ይሄ እንዳለ 0 ዳውት ሲሆን to 128 ይሄ እንዳለ 1 ሲሆን 1 ባረግ ኖሮ in reality in exponentoች like the lowest one minus 127 and the highest one 128 they are reserved for special numbers they're not actually used for like the regular way of representing but that's like maybe a bit out of scope so just have that exponent calculate sarag bias አለኝ 127 for single precision so if I have a particular exponent ለምሳሌ like positive 9 or minus 32 I always have to add my bias to get the binary value in here and then if I have a binary value like my 8-bit exponent floating point representation directly extract ያደረኩት to come back to my original exponent I have to take away 127 just keep that in mind and then the last part is ስንት ቀረን አሁን 32 ቢት ነው in total ያለኝ አንድ ለሳይን ተጠቀምኩ 8 ለኤክስፖነንት ተጠቀምኩ 9 ተጠቅም ያለው በአጠቃላይ 32 ሲቀነስ 9 23 ቢት ይቀረኛል 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 እንደምንም ፊት አድርገናቸዋል 23 ቢት ይቀረኛል 23 ቢቴ is reserved for exponent አለኝ ሳይን አለኝ ማን ቀረኝ ማንቲሳ this is reserved for the mantissa right and the peculiar thing ሁሉም peculiar ነገር አላቸው ሳይን ቢቷ ብቻ ናት uncomplicated ሳይን ቢት 0 ለፖዚቲቭ 1 ለኔጌቲቭ ተባለ exponent the peculiarity is we have a bias of 127 the mantissa the peculiarity is there's always an implicit 1 that comes before right so if በ 23 ቢት እዚህ ጋር ማንቲሳይን እንትን ካረኩ this is 23 bits right like 0101 ምናምን ሊሆን ይችላል whatever the number is I always assume ኮምፒውተር ውስጥ እንደዚህ ቢቀመጥም ለኛ we assume that እዚች ጋር there is a decimal point and then right before the decimal point there is 1 always so if my mantissa is like 1101 that's stored in the floating point I assume it's 1.11010 if it's ለምሳሌ እዚህ ጋር solution ውስጥ የተሰጠው example ይሄ ነው mantissa ይባላል this is 23 bits then I assume there's a 1 an implicit 1 with a fraction point after it and this is the actual value of the mantissa why can we do this because there's two possible values for any bit position አይደለ there's only two possible values way 0 way and if we always assume there's a 1 right before the 23 bits then we're actually representing 24 bits in only 23 bits of space አይደለ because 23 ቢት ሲሰጥሽ አንድ ነጥብ ብለሽ 23ቱን ደርድረሽ 24 ቢት ሪፕሬዘንት ማድረግ ትችያለሽ ማለት ነው። that's because any number other than 0 that I can hope to represent has at least one bit አይደለ? ከዜሮ በላይ ከሆነ ነምበሩ at least አንድ ቢት አለው። so I'll be fine assuming there's a 1 bit before. that means ለዜሮ special representation መፍጠር አለብን for this format, and that's just here for curiosity ራሳችሁ look it up and find it. But yeah, so I always assume there's a 1 bit right before with the fractional point directly after that one. So in my floating point representation, in those 23 bits ማስቀምጠው ማንቲሳ is actually all the digits after the fraction point, all the bits after the fraction point. The one before the bit is stored. So as we've seen demo in the scientific representations in Aura for binary numbers, the scientific representation is always 1 point, a series of zeros and ones, times 2 to the power of some exponent. The always, because we said the non-zero digit, la scientific notation yalno, non-zero digit before the point, the only available non-zero digit for binary numbers is 1. So that's why it's just 1 mihono marathon. Okay. So right, so that's the mantisa. These are the things you need to know before you go about doing conversion exercises, back and forth between decimal fractions and floating point representation in this IEEE 754 format. Okay, so we can now jump right into the questions, and I'll just follow along ziga alone explanation. So ziga ምንድነው, we're given a certain 32-bit binary numbers that are already in the single precision IEEE 754 floating point format, and we're trying to achieve back into decimal notation አይደል? so already ለምሳሌ መጀመሪያ ላይ ሲሰጠን እንደዚህ አይነት ቁጥር ሲሰጠን ምንድነው ማድረግ ያለብን? we divided up into the sections we know about. እዚች ጋር በአረንጓዴ ያለችው ሳይኗ ናት፣ በሰማያዊ ያለችው ኤክስፖነንቷ ናት፣ በኦሬንጅ ያለችው ማንቲሳዋ ናት። so sin b2 ስንት ነው? 1. so we already know this is negative. so what do we know about the number already, just by like taking a glance? That it's a negative number. And then we have the value of the exponent. so exponentaችን binary in 8 bits ተቀምጣለች። እቺን 8 bits binary ወደ decimal notation እንቀይራታለን, right? like እዚህ ጋር and we don't need to go over conversion between back and forth between binary numbers and decimal notation again, but yeah, like quickly እዚች ጋር ማየት ይቻላል። there's 2 ziga 8 አለኝ፣ እዚህ ጋር 64 አለኝ፣ 8 እና 2 10 እና 64 74 አይደል? ስለዚህ በኋላ ይሄንን ላይ ከበር አላደርግም። but the exponent stored የሆነው value 74 ነው፣ the stored value. I say stored because it's pretty important. It's not the actual exponent, it's just the stored exponent. What do I need to do to get the actual exponent from the stored exponent? biasing መቀነስ አለብኝ፣ ምክንያቱም ይሄንን stored ለማግኘት ያኔ ደምሬ ነው ያመጣሁት። so you take out the bias, ከ74 ላይ 127 ስቀንስ negative 53 ያገኛለሁ። my actual exponent is minus 53. so whatever months I end up with, exponent ምንድነው 2, exponent is minus 53, which means I'll multiply whatever I find by 2 to the minus 53. ምክንያቱም ባይነሪ ያለ ነው ማረው። okay, so now we go on to the mantisa. Mantisa is እዚህ ጋር አምጥቼ ኮፒ አደረኳት። ምን ተባብለናል? the peculiar thing about mantisa, there's always a 1 bit with a fraction point right before the value of the mantisa. so here kona stored value, again notice the differences between the stored and the actual values. we're taking some design choices to store our information in a very efficient way. Ayatru, like one efficiency that we've gained is being able to represent a 24-bit number in only 23 bits. Another efficiency we've gained is to express a range of numbers from negative to positive by just using unsigned 8-bit representation, by thinking of an implicit bias ማለት ነው ጭንቅላታችን ውስጥ ያስቀመጥነው ብዙ ነገር አለ for this representation አንደኛው ምንድነው the one dot አይደለ ሁለተኛው ምንድነው the bias amount but anyway so this is the number once you've gotten here you could just convert this into decimal directly there's different orders in which you do things the easiest order is እዚህ ጋር ያለውን ማንቲሳ ቫልዩ የአክቹዋል ማንቲሳ ቫልዩ ስታገኙት ቀጥታ ወደ ዴሲማል አድርጋችሁ በ2 to the power of -5 3 ማባዛት right ከፈለጋችሁ although it will be a lot more complicated you can also መጀመሪያ በ2 to the -5 3 አባዝታችሁ ደግሞ ወደ ዴሲማል መቀየር ይሄንን ባይነሪ ቁጥር በ2 to the -5 3 አባዙ ብላችሁ ምን ማለት ነው you shift this point back 53 times okay but that's it so what do I do now when I convert the above to decimal ይሄንን ቁጥር ይሰጠኛል this conversion is a bit complex yeah maybe some kind of calculator help or converter help መጠቀም ትችሉ ነበር እዚህ ጋር you could also have done it by hand because we've already talked about how you could do this is 1/2 this is 1/4 this is the sosteniao is 1/8 it's like essentially 1/2 to the n ማካፈል ማለት ነው and n is the position right after the decimal point so the measurement is 1/2 ከዛ እነዚህን ቁጥሮች እየደመሩ ይሄንን ኤክስፖነንት ቫልዩ ማምጣት ይቻል ነበር okay so that's what ይሄኛው ወደ ይሄ ይቀራል I have my actual mantissa so the final number will be -1 to the power of the sign bit this is just a shorthand way of saying 0 is positive 1 is negative because -1 to the power of 0 ካልኩኝ anything to the power of 0 is 1 so በአንድ ስናባዛ ፖዚቲቭ ነው ቁጥሩ ማለት ነው ምክንያቱም እዚህ ጋር ያለው እንዳለ like we assume it's positive and if I do -1 to the power of 1 ደግሞ anything to the power of 1 is itself so -1 ይሆን ነበር የሆነ ቁጥርን በ-1 ስናባዛው ኔጌቲቭ ይሆናል so this is just a shorthand way of saying 0 is positive 1 is negative and we already know አንድ ስለሆነ ሳይን ቢቱ ኔጌቲቭ እንደሚሆን ቁጥራችን and then እቺ ማንሳለች times 2 to the power of exponentaችን -5 3 ነው ይሄንን ቁጥር ብቻ ብታስቀምጡ ኖሮ like -1 በዚህ times 2 to the power of -5 3 that's fine because that's still like representation of the number it's still in decimal notation አይደለ because ሁሉም እናቃቸው ነገሮች ናቸው binary ቁጥር አይደል but you could have done this plug this into a calculator and received this number in the proper scientific notation for decimal numbers and that's this እቺን ቁጥር በ2 to the -5 3 ስናባዛ ይሄ ነው ቁጥራችን yeah simple አይደለ actually ስትገቡበት same thing እዚህ ጋር 0 ስለሆነ ፖዚቲቭ ነው ቢቴ እቺን 8 ወስዳታለሁ and then I convert this to its decimal representation its decimal representation is 173 I take out the bias when I take out the bias it's 46 so whatever number you guys have mamataun I multiply it by 2 to the power of 46 note that this time it's a positive exponent so I have positive whatever I have it በዚህ አባዛለሁ እዚች ጋር exponent ናት and then now I take this and I add my implicit 1 bit just to the left 1 dot ይሆናል አይደል once I have this number I convert that to its decimal notation 1.11101 ማለት ምን ማለት ነው እንደዚህ ነው ካልኩሌተር ውስጥ መግባት ይችላል ኮንቨርተር ውስጥ መግባት ይችላል ይሄ ነምበር ወደ ዴሲማሉ ሲቀየር it's this number 1.916 ምናምን so now I have it's positive ይሄ ያለኝ so እቺን ቁጥር times 2 to the 46 አረጋት is እዚህ ጋር እሷን ሳባዛት ይሄንን ይሰጠኛል this is the መልስ right so now we'll do the other way around now we have a number in decimal notation of decimal fraction number and now we're trying to convert that into a floating point representation single precision i.e. 7544 math. So what do I know about the signage of this number? it's positive አይደል? ኔጌቲቭ ሳይን ምንም ነገር አይታየኝም። ፖዚቲቭ ሆነ the first bit, my bit that is reserved for sign ምንድነው ቫልዩ የምትሆነው? 0። እዚህ ጋር አንድ explanation አለች። when we talk about scientific numbers እናወራ አሁን like let's first change ይሄንን ቁጥር to its binary equivalent. እንዳለ ባፌ እንትን አይደለም። let's do when we change ይሄንን to its binary equivalent, it gives us this. Again, we don't need to go over ትዝ እንደሚላችሁ ከሆነ ይሄ ማለት like 2345.326 ማለት equals 2345 plus 0.326 ነው አይደል? And then I can change this to binary in the normal በሁለት ማካፈል ምናምን መንገድ, and I can change this into binary in the normal ማባዛት መንገድ አይደለ? It's like a similar, structurally similar. በሁለት እናባዛለን, I'll get one ቁጥር 0 ወይ 1 ነጥብ something አገኛለሁ whatever እንትን ይሄንን ቁጥር ነው እንደ እንትን የማስቀምጠው እንደ ሪማይንደር የማስቀምጠው 0 ከሆነ 0 እንትን ከሆነ 1 and then ከፖይንት ቀጥሎ ያለውን ቁጥር አመጣና በሁለት አባዛለሁ ምናምን። there's a particular conversion method ለፍራክሽን, but yeah እሱን ተጠቅመን ይሄንን ቁጥር ማምጣት እንችላለን. so the part before the point, the part after the point, right? so now I have this. ይሄንን convert ካረኩ በኋላ remember it needs to be in scientific notation, right? I have already converted this decimal fraction into its binary equivalent, but now I need to put this binary equivalent in its scientific notation, in a scientific form. That means this point needs to be shifted to just after the first or the most significant bit, the most significant one bit, and that's this one መጀመሪያ ላይ ያለችው ማለት ነው. so ስንት ሙቭ አረጋታለሁ? 1 1 2 3 4 5 6 7 8 9 10 11 ጊዜ ወደ ኋላ ሙቭ ካረኩት just after እንትን ይመጣልኛል. so ይሄንን መልሼ by putting the fraction point just after the first one እቺ ትመጣልኛለች ስጽፋት times 2 to the ስንቴ ነው ሙቭ ያረኩት ወደ ኋላ? 11 አይደለ? 11 ወደ ግራ, which means exponent ፖዚቲቭ ነው. በፖዚቲቭ ቁጥር ማባዛት ነው የምፈልገው. ፖዚቲቭ ኤክስፖነንት ነው ማባዛት የምፈልገው, and that's 11 2 to the 11 ማለት ነው. so this part ቆንጆ ከለር ልምረጥለት. this part is the scientific notation of this, and this is the binary representation of the number I gave you originally. okay, so now we have our mantissa. What else do we know about the mantissa? In its stored form, we drop the 1 right before the bit. እቺን drop አረጋታለሁ ምክንያቱም I can just assume she's there, and then I just take 23 bits to the right of the fractional point. Sometimes you might get a number that's more than 23 bits, like ከፖይንቱ ቀጥሎ ምንድነው ሳካፍል ምናምን ያመጣሁት like ለምሳሌ 36 ቢት ሊሆን ይችላል. that's fine, you just take the first 23 and drop the rest, right? you drop the remaining 13. or if I only have like I don't know 5 bits and I need to fill up 23, what do? I just pad with 0. because ለምሳሌ like okay, so if this is my number, my binary number, let's say, if I pad 0 ziga, this is a much different number than this አይደለ? ይሄ በጣም ትልቅ ቁጥር ነው። ግን if I padded after a fraction point, I went out of bound. out of bounds የሚባል ነገር አለ በኋላ እንትላላችሁ. if the decimal point is here and I just kept adding zeros, ምንም ቁጥሩን አይለውጠውም. it's just like adding zeros to the left, right? because this is kind of saying 3 or 3.0 or 3.0000 ሁሉም 3 ናቸው። ምንም ከፍራክሽናል ፖይንት በኋላ 0 ማስቀመጥ ምንም እንትን አያመጣም። So I can, because there is already a fractional point at the beginning that we all assume, I can just pad with zeros. So 5 ቢት ብቻ ካመጣው 23 ለማምላት 0 መደመር ዜሮዎች መጨመር እችላለሁ at the right end ማለት ነው። So that's a little bit on how to like, you know, make it count to exactly 23. እዚህ ጋር just take the first 23 to get the stored value of the mantissa, which is this, right? So I have the stored value of the mantissa, and then now for the 8 bit of the exponent, I have the sign bit already. አይደል positive ቁጥር ነው 0 ነው sign bit. I have my 23 bits for mantissa. ምን ይቀረኛል? The 8 bits for exponent. Exponent is positive 11. ምን አደርጋለሁ? I add my bias. አይደል? Remember, when we're trying to get the stored value, we add the bias. When we're trying to retrieve the actual exponent from the stored value, from the stored 8-bit binary, we take out the bias. So አሁን I add the bias. 11 ሲደመር 127 is my stored value is 138. I just convert 138 into my an 8-bit binary number, and that's this number. So I have my 8-bit. So እነዚህ እቺ እዚህ ጋር plugged in ሆነች. My sign bit is 0. ይሄንን ቀጥታ እዚህ ጋር መጣሁት ደማምሬ 32 ቢቴን አገኛለሁ, and that's the floating point single precision IEE 754 representation of 2345.326. Okay, lovely. ከፖዚቲቭ አንድ ቁጥር ዘል ያለው እንዴ? Okay, so the next one is minus 0.0034. It's a negative number, so my sign bit is what now? 1. And then I would have 0.0034 እቺን ወደ ባይነሪ ቀይራታለሁ. For numbers less than 0, ቅድም ተነጋግረንበታል how to convert to binary በሁለት ያባዙ ምናምን. I've shown you that method before during class, and this is what I get. ማያልቅ አይነት እንትን ነው. You know how some numbers continue. After a certain while you can just stop, because you know you only need a certain amount of bits አይደለ? Like ለምሳሌ 23 ብቻ ነው የምፈልገው ለማንቲሳው. ከአንዱ the first one bit ቀጥሎ 23 ካገኘው በቃኝ አይደለ? ከዚህ ቀጥሎ 23 ካገኘው ማቆም እችላለሁ, ምክንያቱም I know I'm only storing that. ከዛ በላይ ቦታ የለኝም, ከዛ በላይ precise መሆን አልችልም. So yeah, so ይሄንን ስንቀይረው we get this number, you know, for clarity's sake, and as much space ተጠቅመን አስቀምጠናል እዚህ ጋር in the solution. So what do we do now? The point እዚህ ጋር ናት, the first one bit እዚህ ጋር ናት ያለችው. So እቺን point we have to bring her all the way here. እዚህ ጋር ለማምጣት how many times do we need to move it? 1 2 3 4 5 6 7 8 9. I need to move it 9 to the right. If I move it to the right, I know it's a negative exponent. So ይሄንን ቁጥር መልሰን 1.111011 ምናምን አድርገን decimal pointun just after the first one bit አድርገን times 2 to the, what's my exponent? -9, because I moved it to the right 9 times. So this is my final number, right? Without the sign. Now what do I do to get the mantissa and the exponent? Let's start from the exponent this time. ቅድም ከማንቲሳ አድርገናል exponent ያለው. The exponent እዚህ ጋር it's -9. What do I do? I add my bias. What happens when I add my bias? 118 ይመጣልኛል. 118 in binary in 8-bit binary አስቀምጣታለሁ. What's the value I get? This. That's my exponent. Now I have this ቁጥር. ማንቲሳ and stored value ለማግኘት ምን አደርጋለሁ? First, I drop my 1. አይደል? because I'm only working with this. I just count 23 bits just after the point and take that. So it's going to be, this is much shorter than that, right? Because it's just the first 23 after the point. Yeah? 1 0 1 1 1 1 1 0 1 1 1 yellow 23. So that's my mantissa. So now I just stick them together. My sign bit is 1 because my number is negative. Take the exponent I switched, and I take this mantissa value, and this is my IEE. floating point representation. For Zichuga, there's a typo, -1 ማለት ነው. So -1 ቀየርትና that's a simple number, but what will it look like? Negative no, the sign bit is 1. Change the number to its binary format. 1 is 1. 1 was a scientific notation scenario. Point 8 አይቀመጥም because the point is already after the first most significant bit, the first one bit አይደለም. So 1.0 times 2 to the ስንቴ ሙቭ አድርጌዋለሁ ኤክስፖነንቱን ምንም ጊዜ. So exponent 0 ነው. Do you see that? Like you start with 0, and depending on how many times you move to the left or right, you add or subtract. So if I move to the left, if I move 3 times to the left, I add 3. My exponent is 3. If I move 5 times to the right, I take away 5. My exponent is -5. If I don't move the fraction point at all, my exponent value is 0. But 2 to 0 ማባዛት ማለት ምን ማለት ነው? It's multiplying by 1, which means I just leave the number alone, right? Okay. So 1.0 times 2 to the power of 0. So my ምንድነው እዚህ ጋር sin a is 1. My exponent is 0. 0 ምን አደርገዋለሁ? I add 127. 127. 127 I represent it in binary, which happens to be 0 followed by 7 ones. Right? So this is the binary representation of the exponent 0. And then አንድን ደግሞ ወደ ማንቲሳ ቫልዩ መቀየር ነው. 1.0. What do I do when I want to find the mantissa? I drop my 1. 1 in drops አረጋት ከፖይንቱ በኋላ 0 አለኝ. I need 23 bits ከፖይንቱ በኋላ ከሌለኝ ምን እናደርጋለን ተባብለናል? 0 መጨመር. Pad it with 0 because it doesn't change the number, right? Because 1.0 is the same as 1.0000 1.023 zeros. So I just take 23 zeros and take that as my mantissa. Do you see? አንዱ ድሮፕ ይደረጋል ከፖይንት ጨምሮ ቀጥሎ ያሉትን 23 ኔክስት ቢቶች ወስዳለሁ. ቢት available ከሌለኝ 0 መጨመር እችላለሁ because it doesn't change the value of the number. So now when I put it all together, my sign bit is 1. My exponent is this because 0 plus 127, this is the binary representation, 8-bit representation of 127. And then this is a bunch of zeros, which means implicitly 1 point a bunch of zeros, which just means 1. So that's my IEEE 754 single precision floating point representation of -1. Okay, so that concludes our video. Hope this was helpful. Any ጥያቄዎች ካሉ, again, you can reach me. ሄኖክንም reach out አድርጋችሁ. You can request for more explanation videos. Yeah, good luck with studying.